Hello, welcome to the discussion continuation of 8086 microprocessor architectural details. The part 2 session of 8086 architecture description. It will be carried out with the insights of the architecture, some support registers and memory blocks. Then we can have a look over the pin diagram of 8086. The part where we have ended the part 1 is the architecture representation of 8086, where few of the known parts in this block diagram can be understood easily, saying like arithmetic and logic unit, where all the execution shall happen, supported by increased size or enhanced size of some status of indications through flag register. Then some of the registers in support to the processing unit. So if we go on with each block details, we shall start saying like if I show the overall picture of how a represented architecture might be there in 8086 architecture representation, this is some arrangement. This is another way of showing the architecture arrangement. Now if we go for each block and showing the discussion on this block, let us go with the easy things. After ALU, the blocks which show their preference, the very first block we always start to learn will be the arithmetic logic unit, from where the execution starts. Actually, after power generation, clock generation starts, and it is a continuous process like a heartbeat going on in a body of the microprocessor. The other thing that happens after is fetching of the instructions, decoding of the instructions, then execution of the instructions. While learning, we show an easy way of learning through ALU. Connected to ALU will be some set of processor registers as listed in the arrangement here. There are categories of registers which we put under the heading called register organization. The categories are mentioned as general purpose registers, address registers, and control registers. In general purpose registers, we see the names accumulator, B register, C register, and D register. Accumulator is the most prominent processor register, which stands its place at the ALU arrangement. Whenever we don't have any specific location to store our data after the execution, we shall select accumulator as a default result holding register. Sometimes when we have only single data to be given to the ALU, accumulator should be that minimum one register that will be given through the data. Whenever we have two values to be entered, one value definitely will be passing through accumulator to the ALU. In support to accumulator, we have another register B, which is also represented in 16-bit format as BX, in 8-bit format as BL and BH. A very prominent register after the support of accumulator is B register. C register is very normal general purpose register, which is represented in 16-bit format as CX, in 8-bit format as CL and CH. Apart from being a general purpose register, C register is also termed as count register, which is used for loop operation. Another friendly register to accumulator is a D register, shown in 16-bit format as DX, and 8-bit representation as DL and DH respectively. So this register is one of the most prominent general purpose register. Apart from being a general purpose register, it has a specialty to support accumulator in multiplication, division, and port operations. So these are some of the insights and basic things to about the general purpose registers. Few more registers that could be listed under general purpose category are SI and DI. Source index registers used mostly as address registers, sometimes can be used for general purpose operations. Base pointer something that points towards the instruction starting value of the address. It is an address register. Stack pointer, which points to the top of the stack. It holds the address of the top of the stack. Then instruction pointer, it holds the address of the current instruction that is being executed. In support to these general purpose and address registers, we have peculiar address registers which are used mostly for segment operations. We need to know what is the segment operation in further discussion. They are categorized into four representations here. Each register is of 16-bit size, and their names are being classified as code segment address register, data segment address register, stack segment address register, extra segment address register. as well as we have our own flag register which is of size 16-bit size with representation to 8086. So how shall be this flag register identified? If we have a look in comparison with 8085, this was a representation for 8085 flag register. The same register is again given for 8086 with the same positions and most similar names. Now it has been given with an extension up to 16 bits. What are the positions that are being shown are listed in the register arrangement here. Carry, parity, auxiliary carry, zero, sign, trap flag, interrupt flag, direction flag, and overflow flag. This will be the representation of these values here. So carry, which generates at the endpoint of any higher bit value. Parity flag is used to show number of ones generated in the result. Auxiliary carry when it is generated at halfway of the operation. Zero flag indicates all zeros in the result. Sign flag indicates the negative value or positive value of the numerical value. Then a trap flag is used to show the generosity of our microprocessor. It checks for interrupt at every execution of instructions and restarts the instruction if there is no interrupt being requested. This is a non-maskable interrupt which has to be generated after execution of every instruction. Then interrupt flag, if any interrupt is raised, IF will be made to 1. Direction flag indicates the way we are accessing the memory from least address to highest address or highest address to least address. Then we have our own routine overflow flag which shows the excess values in the arrangements. Now this is a clubbed arrangement which we see in the arrow marks of architecture. These are the things that we represent with respect to the pin diagram. All the arrows that we have seen in the architecture are the pins that are coming out of the architecture. So it is a 40-pin IC. Similarly, it has the same representation for power supply and ground arrangement. Pin number 40 is VCC, which works under 5 volts DC. Then it has a ground arrangement. Supported ground arrangement is there again at pin number 1. Then clock arrangement at pin number 19. From there starts some data to address representations here, which is followed on the other side. Then we can see some more multiplexed names that we can discuss in further arrangements. Then we have maskable interrupt and non-maskable interrupt request positions. Then we have a special category of arrangements for the pin 31 to 24, which have peculiarly to work on two modes. One is minimum mode, another is maximum mode. Then we have a very most important friend of ours in the pin diagram representation, reset. Supply, ground, and reset are most common pins we find in any architecture. Then ready pin indicates the working status of our microprocessor to accept the instructions. These are all the representations that show how 8086 has been enhanced compared to its earlier versions, and to show 8086 is most revolutionary microprocessor in the processor technology generation. These are the handful examples to show, like it has multiprocessor mode, then it has physical memory organization mode, then it has memory segmentation arrangement. All these things make 8086 more special compared to its earlier version and more basic design for enhancement in the coming versions. So we'll take a gap here for pin diagram and register discussion. The next part will be continued with some more blocks that are being left in the architecture to discuss. So coming discussion will be on memory segmentation of 8086. So thank you for sharing the presentation.